introduce the aspects or the functions of system services or ancillary services in terms of voltage control by means of reactive power provision, frequency control, by the provision of control power, primary, secondary, and minute reserve, grid operation, and redispatch actions or events in the system. Black start is one of the most important today in Europe. And last not least, I will introduce some aspects regarding markets or opening markets for renewables, providing ancillary service and needed regulations. Yeah. Where are we now in Germany? This is a slide or a snapshot from the week from May 7th to May 13th in 2016. And here you see that at 11 o'clock, roughly 88% of the consumption, of the total consumption in Germany, about 64 gigawatts was covered by renewables, by 27 gigawatts photovoltaics and 21 gigawatts wind. And so there's only a small share remaining for conventional power plants. So this is okay. So they don't pollute carbon dioxide, but who is maintaining system services? Who is providing system services? This is one important question we have to think about and we have to find answers in the future. What will happen with conventional power plants in the future? This is a result of a study, so-called LIGHT or lead study for the development of Germany in terms of renewable development. And here you see the frequency distribution of the full load hours of the conventional power plants or combustion-based power plants in Germany. You see here we have still some nuclear power. Germany decided to close all nuclear power stations at the end of 2021 or in the beginning of 2022. So this is more or less the past. And then we have some full load hours here, or followed by brown coal, black coal, and here we see biogas, biomass power plants. So they are in operation here. Biogas, biomass power plants are in operation in mean of 6,000 hours per year. So this is economic. Brown coal has a mean power duration of 7,500 hours per year. This is economic, no shutdown, still operating constant, and this is an economic value for brown coal power plants. Then we have some others, and you see different full load hour frequency distributions. This is the situation today. But what will happen in future? We have this situation in 2050, expected in 2050. Only the sustainable power source biogas is operating still with a mean full load hour of 4,000 hours, and all others, so nuclear is phased out, all others have full load hours of about 1,000 to lower of 1,800 to 1,000. So we have conventional power plants still in operation, but only for a short time, a short period in the future. And this leads to the question, is a secure grid and system operation with nearly 100% renewables energy sources feasible? Who is maintaining frequency and voltage control in the future? Stability of the grid means voltage stability maintained by voltage control. This is the ancillary service assigned to voltage control. And we have voltage management, reactive power provision, compensation units, and tap changers. And here you see large deviations of voltage below or above predefined limits need to be avoided to have a stable system. On the other hand, we have a synchronous area, and here we see the same situation. frequency control is one important aspect of a stable grid, and we also need to avoid deviations from the predefined frequency of 50 Hertz or 60 Hertz. It depends on where the system is operating. And then we have another aspect or another function. It's the so-called rotor angel stability. I will not go into detail here. These are some different aspects, but here we have also solutions, but I will not go into detail for this aspect. To elaborate and simulate and assess a future system, we developed a so-called renewable combined power plant. This is a simulation model simulating the German and the European power system in the future based on 100% renewable energy provision. And here you see the future grid system of Germany, and blue bubbles mean we have injection from wind, for example. Yellow means injection from photovoltaics, and green means injection or power production from biogas, biomass, and red means we have more consumption than production at a certain grid node. So the system is the German transmission grid, where the grid stability is the most important question. So to go into detail, we simulated the temporal characteristic of the energy supply system in detail based on weather-dependent generation with high-resolution historic weather data and physical plant models from turbines, wake effects, orientation, inclination, and so on. Detailed models for the demand, industry demand, industrial demand, households, and others. We used standard load profiles, we used load management strategies, and we added and modified the balancing systems based on bioenergy storage systems and methane power plants. Methane is a technology to produce hydrogen from energy surplus or from wasted wind power, for example, and then to mix it with carbon dioxide and to produce methane, which can be injected in the German gas pipeline system. And also we have a result of, or we modeled the load flow animation to see what will happen in the future and what's about the extreme scenarios. It was not our focus to simulate the overall system and the characteristics. We focused on extreme scenarios with high wind speeds, low demand, and other extreme scenarios, and what will happen with the electric system in the future when only providers from renewables will control frequency and voltage. For frequency stability, we simulated a power outage of 600 megawatt for each 15-minute situation for a longer period for more than 1 year in Germany. And we looked what will happen, or we elaborated what will happen when there are more and more inverters injecting to the grid, and not when there are less direct coupled synchronous generators. So less rotating mass will lead to the situation that the frequency decreasement will speed up, so the time constant is lower, and you see we will go below 49 Hertz. This was our limit. We like to be below 49.2 Hertz to avoid frequency damages. And you see in the future all frequency dips happening whenever lead to a decreasement of frequency below 49 Hertz. How to cover or how to avoid this situation. One aspect is to have a certain amount of rotating mass in the system. There are some solutions in Germany. These solutions need to be further developed. For example, nuclear power plant phased out can be used as phase shifters, as rotating mass, or as rotating reserve in the system. On the other hand, a faster primary power control and faster response for primary power will give or will include solutions to solve this problem. And here you see different contributions for different situations, more windy situations, more sunny situations, and all these situations lead to realize or to not to endanger the system with a frequency below 49.2 Hertz. And you see when you have a fast primary reserve power contribution by PV, electronics, electrolyzers and batteries, you see the yellow reaction contributed by wind power. This is here the blue one, and contributed by methane, pump storage, and other like biomass, biogas power plants. This is the green one, and all fast responding primary control power providers are able to solve this problem. But here we have still a very fast decreasement. Here we need some remaining rotating mass in the system. Okay. About the realization, are wind power plants or wind farms able to provide control power? We set up a big demonstration with large wind farms. Here we see 26 megawatts. It's the nominated power of the wind farm, and here we demonstrated the primary control power provision and injection for negative primary control power, for positive primary control power, and then the plant was released from the provision, and also frequency dependent following the frequency. And here we have the same situation for secondary control power, where some other time constants need to be recognized. So this demonstration has shown that wind farms can provide control power. Not only one single wind farm, but a group of wind farms widely spread can provide control power as needed today, with the same regulatory aspects as for conventional power plants. The next aspect about voltage control and congestion management. For this challenge, we assessed the future situation and detected the reactive power demand for voltage control in the transmission system by AC load flow calculation. And it was shown that the reactive power provision by estimation of impact of connected power plants was realizable. So the existing renewable power plants can provide enough reactive power, or can cover the reactive power demand to realize voltage control also in future. For congestion management, we have also simulated all situations in Germany for the future scenarios. And here we detected some congestion areas also in the future grid with grid expansion. And these congestions can be avoided by decreasement of power injection on the one side of the affected line, and an increasement of power production on the other side of the detected power line. So this is also not a challenge. It needs, or the need is to have a more flexible grid operation, but the German grid operators are now maintaining the grid very flexible. Redispatch measures are in their daily operation. So this is not a challenge. This is today a daily task and also in the future. About voltage control by renewables, you can see here what we developed is a system to operate or to provide reactive power, not only to realize certain predefined values or set points at the point of the direct connection of the wind farm, but also to provide control, to provide reactive power to maintain the needs or to realize the needs of the TSO. And here you see when we have power flows outside or injection into the transmission grid, we have capacitive reactive power needs, and when we have load, more load than production in the lower voltage level, then we have inductive power needs, reactive power needs, and this reactive power needs can be maintained or can be realized by a so-called wind farm cluster management system. So distributed wind farms in the lower voltage grid, in the distribution grid, can be operated by realizing set points sent from the system operator, and the system operator is provided with an overview of his 110 kV or below or lower voltage kV system, and can ask or request several set points or several amounts of reactive power to maintain the 110 kV grid, and also to support the higher or extra high voltage grid. About, I mentioned about the redispatch events in Germany. You see here that there is a very large increasement of redispatch measures in Germany. We have about, in 2010, we had about 1,500 or 1,600 redispatch events. In 2050, we have 10 times more events, and redispatch means to reduce conventional power plants on the one hand, on the one side of the congestion, and to increase power production on the other side. And this is very cost effective, and you need to optimize these redispatch events. And so we developed an optimizer to combine different knowledges to realize optimal power flows and to realize an optimal decreasement and increasement of power injection of conventional and renewable power plants. And this model results in a very cost-effective and technical optimized redispatch organization. Here you see how this works. We have a congestion detected here, decreasement and increasement of power, and this leads to salvage or to a solution to avoid this congestion. And this is not in operation today, but will be used in the near future by the German TSOs to optimize their redispatch. One of the most important tasks or challenges is a restart or a black start after blackout. So all TSOs or system operators are fearing blackouts. They don't know exactly if the restart is working. It's one of the most important tasks of the TSO to recover a system after a total blackout. And in the past, the blackout procedure was organized like this. A single power plant combined with a load was started or restarted, and then they expanded the area and connected different power plants and different loads to have a stable frequency. And last not least, we see here the frequency is recovered and the system is recovered. So the integration of renewable plants in backstart concepts is a major task of a new project in Germany. What will happen when we add not only backstart capable power plants, conventional power plants and loads? What will happen when we add renewable power plants like wind, solar and combined power plants? It is organized like this. We have different areas. So wind farms can provide or can support backstart procedures, solar power plants as well, and other renewables as well. And then we have this situation that when we have different islands, and last not least, we can recover the system in the same manner like in the past. How this can work is shown in this example. Here, a wind farm supports the restart of a steam power plant. Here we have a steam power plant starting up. The load is taken from a hydro pump storage system, and the wind farm itself is used to smooth or to avoid frequency dips here below 49 Hertz. You can see here this is the reaction of the system only with the gas-fired power plant and the hydro power plant. The other curve is the reaction of the wind farm supporting the system without PF control, power and frequency control. And you see here with power frequency control, the system avoids a frequency dip below 49 Hertz. So renewables can support black start significantly and can avoid damages in the system or can support the restart of a blackout. About markets, for ancillary services, we need incentives. So it's not for free. Ancillary services have an effort, or provision of ancillary services has an effort for wind farms or for photovoltaics or for batteries. So they need some incentives, they need some income. And we need to open the markets, control power markets, and we need to define voltage or reactive power markets for renewables, but not only for renewables. But first of all, we need to open control power markets for renewables. And the obstacle or the important hurdle is the product length. So the pre-qualification rules in Germany say you need to provide control power for a certain period, days ahead. And when you shorten this product length, you can see here, this is an evaluation with different scenarios, wind onshore, wind offshore, combination of wind onshore and offshore. And you see when you are shorten the product length, when you are more flexible on the control power market and on the requesting of control power, you can provide more reliable power with wind farms or with PV. And here you see the level of reliability. This is a used figure in Germany, 99.994% reliability for control power. And you see that offshore wind of 1 gigawatt is able to provide more than 60% of the available power for 1 hour in advance. So we need more flexibility in control power markets. We need some new designs of ancillary service markets, and we need better incentives for the providers for ancillary services. And here you see what will happen when we go intraday. It increases the available amount for control power enormously. When we have a very flexible control power market intraday, like the intraday energy market, it increases the reliability from wind farms and other renewables, and will help renewables to give or to have or to get incentives. So, conclusion. What I like to conclude is that a safe and stable 100 renewable-based energy supply or power supply is technically feasible if renewable energy generation, storage and backup power plants with renewable gas, for example, interact flexible and intelligent. For frequency stability, the raise of average control power demand is not expected due to new type of dynamic dimensioning and can always be covered easily in the 100% renewable system. And the reduction of rotating mass by increasing use of converter systems can be compensated by the rapid deployment of primary reserve power due to renewable energy suppliers. Voltage controlled reactive power demand will always be covered, possibly with additional compensation systems in consumption centers. And distributed generation systems, renewable-based generation system, can be used to compensate the inductive reactive power demand of the loads. Flexible generators and storage devices need to be positioned and adapted to minimize grid loads. So we need some flexible power plants at points where congestions are recognized, and the limits, this limits the redispatch and grid expansion efforts. Multiple N-1 bottlenecks can be